So today we will discuss about uh, chapter number 2 in module number 1, program and network properties. So this is your second chapter in module 1. So totally there are 3 chapters from the textbook for module 1. So we are starting today with second chapter, and here we will learn what are the conditions needed for parallelism, how to achieve parallelism, uh, theoretically as well as practically. So first we will take up data and resource dependence. So data and resource dependence is again identified by with the help of data dependence graph. So we will draw a graph so where each node represents statements, program statements, and we will identify parallelism uh, by comparing the statements. So basically there are 5 types of data dependence. One is flow dependence, anti dependence, output dependence, input output dependence, and fifth is unknown dependence. So here what we are trying to do is we are trying to find parallelism among the program statements. Again, there can be different types of data dependence, and in this book they have discussed about 5 type of data dependence. One is flow, anti dependence, output dependence, input output dependence, and unknown dependence. So we'll discuss each one with an example now. So first we will discuss about flow dependence. So flow dependence, so if you can think a statement S2 is flow dependent on statement S1 if an execution path exists from S1 to S2, and if at least one output of S1 feeds in as a input to S2. So flow dependence is denoted as S1 arrow mark S2. So think that there are two statement S1 and S2, and flow dependent is nothing but whenever there is an execution path exists from S1 to S2, and if at least one output of S1 feeds in as a input to the S2. So usually S1 arrow mark S2. So flow dependent is denoted by arrow mark. So time being you will not understand what it is. So next slide we have an example, so we'll understand. But you have to remember, if there are two statements in your program, that is two instructions, you can think like two instructions. So we are denoting flow dependence by arrow mark. Similarly, we have anti dependence. So an anti dependence statement S2 is anti dependent on statement S1 if S2 follows S1 in program order, and if the output of S2 overlaps the input to S1, a direct arrow crossed with the bar, as in S1 arrow with the dash line, dictates anti-dependence from S1 to S2. So again, this is quite difficult to understand from the statement, but anti-dependence is denoted by S1 arrow mark dash S2. Again I will explain this with an example. Here again statement S2 is anti-dependent on statement S1 if S2, like this S2 follows S1. So here S2 is appearing after S1 in program order, and if the output of S2 overlaps the input to S1. Okay, so this is quite confusing now, because once you see the example, then only can understand these statements. But here we have to represent flow dependence is denoted by arrow mark, and this one anti-dependence. Okay, similarly we have output dependence. Two statements are output dependent if they produce the same output variable. Again it is denoted by a small circle with arrow mark. So this is an output dependence. So next we have input output dependence, where input output differs not because of the same variable but because of the same file referenced by the input statements. So we will check all the data dependencies with an example, then you can understand what these statements actually are. Okay, shall we move to the next style? Okay, next we will take a sample example. You can take it as a code fragment consisting of 4 instructions. Here we have 4 instructions. So S1, S2, S3, S4. Okay, and you can think of each instructions as a statements here. In first instruction, load R1 comma A. Load R1 comma A is nothing but, so A you can think of it as accumulator. So from memory we are transferring to register R1. We are storing the data from memory A to R1. Similarly, in second statement we are adding R2 comma R1. So R2 comma R1 means here R1 and R2 are added, the data present in the R1 plus R2 is added, and result is stored back to the R2. Similarly, we have move R1 comma R3. So we are moving the data present in R3 to R1. Then store B comma R1. So we are storing R1 value in memory B. Okay, these are all assembly language instructions you already learned in microprocessor as well as in CO as an example. But now in 7th sem we are not only in the position to understand these programs, but you should be in the position to exploit parallelism. Suppose if you don't apply parallelism to this program, uh, so you have to execute each instruction one by one. Suppose if you exploit parallelism, if you execute 2 or 3 instructions at a time, then the execution speed of the program is reduced. So the purpose of this subject is to, this chapter is to exploit parallelism in the program. Okay, now we will solve this problem. So totally there are 4 statements, so we will write 4 statements. Okay, so first we will write S1, then we will take S2, then we will take S3, then we will take S4. And if you observe here, so first statement is load r1 comma a, and second statement is add r2 comma r1. So first we will only think of flow dependence. So first we will think of only as flow dependence. So flow dependence is nothing but, if you see r1, so output of statement 1 is used as a input to the statement 2. So there is a flow dependency. Then we will write a arrow mark here. Similarly, compare S1 with S3. So in S1 we have output as R1, but here we don't have any input, so no problem. Again compare again we are using here R1 as an input to the statement 4. So again S1 and S4 are connected. Similarly, you can observe in S3. So you can observe here R3 is dependent on, so here R1 output, okay, is used as a output of S3 statement, that is move R1 is used as an input here. So there is a flow dependence. Again you write an arrow mark. Similarly, if you see for output dependence, so statement 1 and statement 3 are both writing to the same register, that is R1. R1 is the output in both the statements, so we can write it as a bubbled arrow. So this is output dependence between S1 and S3. And similarly, we have anti-dependence between the S2 and S3, and you can mark it as arrow mark with dashed line. If you observe here, output of S3, that is R1 output, it is used as an input in the previous statement. Okay, so this is anti-dependence. Anti-dependence means in previous statement the input should not be used as an output in the next statement. That is called as an anti-dependence. Okay, so this is a simple diagram. This is called as a dependence graph, and if you observe here, so finally we will get this output. So you can now think of these statements. Flow dependence now nothing but is if statement S1 execution path exists from S1 to S2, if at least one output of S1 feeds in as an input to the S2. Okay, and if you think here, okay, this output is fed as a input, and that's why there is a flow dependence. Similarly, in anti-dependence, I told you that output of the current instruction should not be the input to the previous instruction. Then it is an anti-dependence. Output dependence means writing to the same register. And if you observe here, S1 in R1, we are writing R1 is output here. Here also R1 is output. So both statements are writing to the same registers. If you try to move this instruction, try to execute this instruction above before this one parallelly, then there will be a problem in the logic. So this is called as output dependence. Okay.